DSO grid services, and looking at the potential value and routes to market for this technology. So in the next 20 minutes or so, I'm going to give you an overview of some of the research work that we've been doing as a university. And also, I'd like to capture some of your feedback. So I encourage you to use the live discussion features. I'll be posing some questions at the end. You're very welcome to ask questions as we go along. I've also put a couple of polls in the chat, which you'll be able to see, just to get an idea of some of the thoughts that you've had, some of the thoughts that you have about some of the questions that we've been trying to understand as researchers working on this topic. So yeah, I encourage you to use that. There's also an upvote facility on questions and answers, and I'll look at the questions as I reach the end of the presentation. So just to introduce myself, my name is Ben Bowler. I'm a Senior Research Associate at Lucerne University of Applied Sciences and Arts. And we've been working on this topic within a project called the PACE project over the last 2 years. So what is the PACE project? I'd like to start by giving you just a short introduction to the project. It's a €90 million public-private funded project that's been co-funded by the Fuel Cells and Hydrogen Joint Undertaking, FCHJU, in Europe. So it's a 5-year project, and during the project, more than 2,800 next-generation fuel cell-based micro-CHP units will be deployed in 10 European countries. So within the project, we've got a number of leading European suppliers, and the focus of the project is on homes and small enterprises. And within the project as well, we've got other partners, utilities, associations, consultancies, and academic organizations, and I'm representing one of those today. And those are providing specific expertise on certain horizontal topics within the project. Within the project, Lucerne University of Applied Sciences and Arts is looking at modeling earned value from the participation of micro-CHP in grid service markets. And I'll focus on the results of some of that during today's presentation. So just briefly looking at the technology then, fuel cell micro-CHP is an in-home technology. Certainly that's the focus of this project. And the technology provides both heat and electricity from a cogeneration unit. At the moment, natural gas is used as the primary fuel source. However, as we decarbonize our gas grids, there will be scope to move to renewable hydrogen as the fuel source, and that's certainly the intention. However, even based on natural gas, there are benefits to the consumer in terms of high energy efficiency, energy savings, and flexibility in terms of time of use of electricity. There's also ongoing work where manufacturers are looking at integration with home energy management systems and integration with forms of storage, such as thermal storage, which is already integrated, but also looking at electrochemical storage and photovoltaic systems. So that concludes just a very brief overview of the project. I'll now give you an introduction on what I want to cover in this workshop, in this presentation. So I'm representing the Competence Centre for Business Engineering, in particular the Energy Economy Research Group at Lucerne University of Applied Sciences and Arts. And we cover various topics within the research group, so looking at feasibility assessments, grid impact analysis for innovative markets, looking at techno-economic analysis, market analysis, and market design, just to some of the topics. And within this project, we've been looking at enhanced roles for micro-cogeneration and looking at the roles that those micro-generation units could play in energy markets. And in particular, the focus of our research has been looking at the earned value, doing earned value analysis for micro-cogeneration, and looking at how that value can be derived from TSO and DSO grid services. What I want to cover in the next 10 minutes or so is the microgeneration as a form of flexibility. So I'll give you a quick overview of that. The grid services, the opportunity to participate in grid services, to look at some of the results from our own value analysis that we've conducted, and looking also briefly at a roadmap. This is work that's in progress. It's not yet been published, but I wanted to give you some early indications of our interim results for that. So this is the roadmap for the micro-cogeneration, its integration into virtual power plants. So those are the topics that I will cover. As far as the earned value analysis goes, we've been looking at additional income from participation of micro CHP in grid service markets. So we want to understand the qualitative and quantitative factors that affect revenue. And we've conducted that analysis for 3 markets. We've looked at Germany, and we've looked at Belgium, and we've looked at the Czech Republic. And we've done things like look at the hurdles to market access. We've looked at roadmaps for integration of the technology into virtual power plants. And we've also calculated the earned value from the avoidance of grid extensions in distribution networks. So just looking at micro CHP as a source of flexibility and where that flexibility comes from, the diagram on the right-hand side is from one of the partner manufacturers in the project. And the numerical values on the left-hand side are given as guidance, and they come from manufacturer data sheets, and numbers would differ from one manufacturer to the next. The flexibility in this unit comes from being able to modulate the micro CHP, being able to modulate the auxiliary gas burner, using the hot water tank that's shown on this slide as a buffer, as a source of storage. And we're also able to use the thermal inertia of the building as a source of flexibility. The thermal inertia of the micro CHP and the system, the installation as a whole, allows us to decouple thermal demand in electrical production. It allows us to shift electrical production to times when it's most valuable. It allows us to optimize the micro CHP activation to allow optimal self-consumption regimes to be established. And they're also able to offer the remaining flexibility to the grid operator in grid service markets when they exist. The thermal storage is the storage that we've been using in this case, both the building and the tank. This is obviously a low cost, low technology, low environmental impact form of storage. And as I said, it's also possible to integrate the system with other forms of storage. In terms of the markets that we've been looking at, so we considered both TSO and DSO grid services markets. We treated grid services in quite a broad sense, looking at different routes to market, looking at market opportunities and the services that the device could offer. However, after the initial investigation, we decided to focus mostly on TSO services. In particular, we wanted to choose, we chose secondary and tertiary control as the two markets for study. There were a range of reasons for this, but the most important reasons were the suitability of the devices for participation in these markets. So things like the speed of the devices, reaction time, the hold time, duty, modulation, and the impacts on the technology itself, things like the stack life. And we also considered revenue. We also considered the maturity of the markets. So although DSO markets are maturing and becoming established in certain countries, they're certainly not well established yet. This means that there's a limited market access for this sort of technology. And it also means that there's limited data available, historical data on those markets. And when you're wanting to do numerical analysis on the potential revenue from these markets, it's important to have that historical data. So yeah, as I say, we ended up focusing on secondary and tertiary control as the 2 markets for simulation. In terms of what we simulated, first we used various simulation and optimization tools to model consumers and self-consumption. And firstly, we started off by modeling a typical home. So we looked at predicting energy consumption patterns, and then we tried to optimize the self-consumption policy. So we built a model of a house, and then we built a self-consumption policy around that. Then we used data sources like the NSOE transparency platform, TSO websites, and some quite detailed collaboration with aggregators. We were then able to build up an understanding of the revenue streams for the chosen markets. We chose Germany, Belgium, and the Czech Republic. We used a multi-criteria evaluation for that. Germany was chosen because it was linked to a previous project that looked at this particular area that we were involved in, the Ennefield project. Belgium was chosen as the policies and tariffs supported self-consumption and flexibility. And there was also good data availability. That was the case also with Germany. And we chose Czech Republic as a comparative case. And this was something that came out of the analysis that we did. It was seen that Czech Republic was interesting, both because it was allowed us to study a more emerging marketplace. So that compared to, say, a more established grid services marketplace like Germany. And we were also able to draw a comparison between Western Europe and Eastern Europe, and the different energy mix dynamics and so on that were present there. So things like spark spreads, for example, are different between East and West, and that could be reflected in our analysis. So regarding the self-consumption policy optimization, we looked at the potential savings that could be realized by the homeowner, and the savings that were achievable in the different countries are shown in the graphs on the right-hand side. So the blue and orange bars, they show the difference between self-consumption with and without the device through an optimal self-consumption policy. The blue shows without micro CHP, and the orange shows with CHP. So if we consider Czech Republic as an example, for a single family house, the OPEX savings from installing a 1.5 kilowatt fuel cell are around 450 to 550 euros per year. For a small industrial customer with high degrees of self-consumption, OPEX savings are between 900 and 1100 euros per year. So just to explain the acronyms on this slide, PEM and SOFC refer to the different fuel cell technologies, and SFH refers to single family house, 3FH refers to a multifamily, 3-family house. And we use that as a way of also of looking at larger households, and also as a proxy for understanding small commercial or industrial units. So yeah, that explains the acronyms. Compared to Germany or Belgium, the figures for the Czech Republic were relatively low. The savings, the spark spread in Czech Republic was different to Germany and Belgium. The gas prices are higher in Czech Republic, while electricity is cheaper. So there's a bigger penalty for shifting towards using gas as the primary fuel, and there are lower government subsidies also available in the Czech Republic. In Germany, good spark spread, local subsidies, direct support for self-consumption was also available, so that supported the case there. And Belgium, it was similar, and there were no green certificates in the region that we studied for OPEX support, but electricity purchase was possible by the DSO, and that helped support self-consumption. This slide summarizes our investigations related to the potential income from grid services. So we considered a wide range of factors, as I said, and we ended up with secondary and tertiary control as the markets that we wanted to study. And then we looked at the percentage additional benefit that could be obtained from offering residential flexibility to grid services markets. And that was a percentage of the final cost of electricity after the self-consumption was taken into account. So if we take the PEM single-family household scenario in Germany as a numerical example, the income for AFRR for secondary control was around between 50 and 60 euros per year in that particular case. And so when you take that 50 euros per year and you apply it to the lower value after self-consumption of the energy consumed over the year, and then that gives you a percentage, and it was around 6.5% additional savings. So you had a certain level of savings that you got from self-consumption, and then an additional 6% of savings on top of that, resulting from potentially from selling your flexibility into the TSO grid service market. So it offered a small additional benefit in addition to self-consumption. So there are a few other things that were important to note. The opportunity costs for using electricity and gas during the positive and negative utilization were reflected in the work. We excluded any costs to do with the effect that would have on the technology, so stack aging, the additional effort for metering infrastructure. The idea was that you'd use existing metering infrastructure that was available in the premises. And also we didn't include the splits between residential income and the aggregator income in this analysis. And that was a fair assumption because that's actually reflected in some of the business models that are used in micro CHP or micro flexibility integration into virtual power plants. For Germany and for Belgium, the revenue was much higher compared to the revenue for the PEM single family house was higher compared to the other scenarios. And this is down to the different operating regimes and the constraints on the technology types. And specifically, the PEM must be regularly deactivated to avoid overheating in summer. And that gives you much more flexibility to use the PEM for flexibility during the summer period. So that reflects that those differences. Yeah, so that gives you an idea of some of the results that we got from the analysis of the different markets. Should mention the income for the Czech scenarios is substantially higher than for Germany or Belgium. This is due to differences in the local market structure in Switzerland. The balancing income in the Czech Republic is mostly made up of availability premiums. So the pro rata activation scheme for the utilization in the Czech Republic is not a contributing factor to the income difference. So things like market prices for availability in the Czech Republic were higher, and that could be accessed by the device. So that gives an explanation of why the percentage savings were better. So yeah, just to conclude briefly, thermal storage from the hot water tank and the building inertia give us a source of flexibility that we can use. And self-consumption provides the greatest benefit. However, there's a side case, an additional case that can be provided from balancing markets if you have access to a device like a micro CHP. What we found was that local conditions have a strong impact on benefit for both the self-consumption and the balancing market revenue. Okay, so I'll now move on to the second part of what I wanted to talk about. So I just got a couple of slides on the roadmap that we're looking at. So it's all very well having the flexibility, but you also need a route to market for that flexibility. And in the final part of our research, we want to understand how additional revenues could be realized. So this work isn't published, but I'll give you an idea of some of the interim results that we have. So we were tasked with investigating a roadmap. So we run a number of semi-structured interviews with aggregators, understanding the current and future technical requirements. We ran a number of semi-structured interviews with manufacturers of devices to understand their technology readiness and the R&D activities that they had in plan. We also conducted a selected literature review, looking at case studies, technical literature, and some published documents like the balancing guidelines. And then we conducted a qualitative analysis where we looked at gaps between requirements and technical readiness and the prioritization of those gaps. And what we'll end up with is a roadmap which will describe how to bring technology like micro CHP with a particular focus on micro CHP for this research into virtual power plants. As part of the work, we investigated the readiness to participate in grid service markets, and we've proposed a series of levels. So the table you see on the right-hand side here is an appraisal of the requirements that an aggregator has and the technical readiness of the equipment manufacturers and equipment owners. So if you've got a high readiness, it means it'll be very easy for you to be connected to a virtual power plant. And in the report, we will define a scoring system that allows manufacturers to assess their technical capability against requirements. And these have been developed with micro CHP in mind, but the criteria could also be applied to other forms of flexibility. So at the most basic level, you have remote control, modulation, smart meters, remote access to the device. These are absolute minimum for participating in a virtual power plant. Where devices start becoming more ready to participate in a virtual power plant is when they have things like a good level of operational duration, 1 to 4 hours, less than 6 minutes ramp up time, so they can respond to requests from the aggregator. They might have less than 5 minutes response time. That's important for primary and secondary control, or 15 minutes response time for tertiary control. And there's some level of more secure direct communication that takes place for example, through a VPN with the system of the aggregator. Manual activation is also possible, but when we start looking at the higher readiness, automatic activation is preferable. When we look more at the higher readiness to participate in a virtual power plant, we look at things like defining the operational rules with the aggregators. So this is a shared understanding of operational rules that will be developed with between a technology developer and an aggregator. IoT capability. So there's a lot of interest in integration of this technology in home energy management systems. This allows things like data collection, transfer of data, monitoring and privacy and security and so on, and also real-time data measurement and communication. And finally, just some other points, other extracts from the analysis. So looking at micro-scale units. So we've spoken to aggregators that have managed to successfully integrate these sorts of micro-scale units in their portfolio. But that aggregation really only takes place when you have over 1,000 units and you're able to aggregate those. And so there's critical mass is really important. The economic viability of flexibility is better when it's integrated with a more established technology like home energy management systems, and the reaction time is really, really important. So this is a real barrier for technology which is able to react more slowly. That affects also ramping and modulation. There are a number of perceived barriers as well. Equipment manufacturers believe that there are a number of things that are barriers to them integrating their technology into virtual power plants. So things like flexibility size. There are examples of 1 kilowatt, 1.5 kilowatt devices being successfully used in a virtual power plant. So size doesn't necessarily matter in this context. Standardization also isn't as big a barrier. So aggregators are able to use existing standards, IOC 104, Modbus, etc., to integrate devices. And cybersecurity also is not a significant barrier at the moment to integrating these devices. So that brings me to the end of the roadmap part of what I wanted to present. Just to conclude, just to like to emphasize that aggregators are considering smaller asset types, and residential flexibility can be part of a virtual power plant's portfolio, and that's been proven in certain cases. The technical barriers are more strongly linked to the market settings than the technology maturity itself, and things like response times. If these could be relaxed, then it would make integration of these sorts of technologies better or more simple. This is also the case for things like electric vehicles. So for primary response, where you start looking at vehicle to grid, relaxing the requirement from 2 seconds to 5 seconds would allow the sorts of cloud-to-cloud communication to take place that would improve the integration of vehicle to grid technology. We do need economies of scale, and although standardization at the moment isn't a big barrier, standard protocols or new standardization efforts would be useful to reduce things like administrative or technical burdens, and that would affect both manufacturers and aggregators. So that brings me to the end of my presentation. I had a few discussion points that I wanted to propose. Also, there's an opportunity if people would like to ask questions for them to do so. So I would invite any questions. Also, if you would like to participate in the poll, then by all means do. A couple of questions to ask in the poll. So one of the questions that we've been trying to understand is how long it would take for small scale devices to participate in grid service markets. And so we've had a mix of responses through the research that we've done. I'm interested to hear people's responses on this topic. So to see whether you think that this sort of small scale flexibility could participate in the short term, 5 to 8 years, 3 to 5 years, 1 to 3 years, or indeed longer than that. I'm also interested, just at the high level, there's only a certain amount of flexibility in this polling, but interested to see whether you think that the biggest barriers to micro CHP and other micro scale flexibility actually participating in virtual power plants and in these sorts of markets, and whether that's down to legal issues, financial issues, or procedural issues. And so I'm interested to hear your thoughts on that. And then if there are any changes, specific policy changes or legal changes, then I'd be interested to hear those in the chat. And also interested to hear your thoughts on what the best form of flexibility could be for grid service markets. And if there are any questions, I'm happy to answer those as well. Okay, I'm not seeing any questions. If anyone would also like to join live and ask any questions directly, then I believe that I could also promote you. So I can invite you onto the stage if you'd like to do that. So that's also a possibility. Okay, well, if there are no further questions, then thank you all very much for joining and for listening to the presentation. I'm available on the email address that's shown on the screen now if you'd like to get in touch and learn more about the research, or if you'd like to be involved actually in the research and participate in questions related to roadmaps and so on. We're also available to discuss that with you. So, okay, so thank you very much.
Hello again. We have one question in the chat. I see.
Which survey are you referring to? So just to give you an idea of whether or not our results will be published. So the results of the earned value analysis that we've done on the potential revenue for grid service markets, that is a public deliverable as part of this this research. The roadmap that we're in the process of producing, parts of that will be made publicly available. The detailed report that we're producing is aimed at the manufacturers, and so the detailed analysis will be confidential for the consortium, but we will also work with Cogen Europe to publish the parts of those that are relevant to policymakers, to manufacturers outside the consortium, and to others that are interested in flexibility. So we will, as I've done today, we'll make parts of that public, and that will be available through the PACE project.